you're fine. You ready? Problems involving momentum and energy. Or let me say this differently. Problems where there's a collision or explosion and where there's a change in height, change in speed. Yucky, curvy path. So what do you want to keep in mind? What to use when? I wrote down here, work and energy concepts can be used together with other mechanics concepts to solve more complex, cooler but tougher problems. Important points to keep in mind. We apply momentum conservation to collisions. That's where we write the sum of all the momentum initial equals the sum of all the momentum final. We use energy to analyze pendulums, ropes, swings, and curved ramps where there's a change in height. That's where we're going to go with KE initial plus PE initial equals KE final plus PE final plus heat if they mention heat, but we'll deal with that later. And the last thing, a complex problem must be broken into steps. So here's a great example. This is a very famous physics problem called the ballistic pendulum, shooting a bullet into a block of wood. I don't know if you've ever asked yourself, before we invented radar guns and things, how the heck did they figure out how fast bullets were traveling? What did the FBI or the RCMP do for ballistic forensics back in the 1940s and 30s and 20s? It's not like you can human time and stopwatch a bullet. Can't react that fast. They used something called a ballistic pendulum, and here's a little picture of it here. We have a 20-gram bullet coming in. The 100 meters per second is way too slow for a bullet, so can you do me a favor? Let's cross this out and let's make it 200 meters per second. Even that's a little slow, but that's a little better. We're going to shoot it into a block of wood, and it's going to stick. What's going to happen then is the block of wood is going to swing up. And using a camera, because we had cameras back then, we're going to film how high it swings up. Okay? We're going to fire a bullet. Now, in this question, I've told you the speed of the bullet, it's going to stick, and I'd like to know how high the block will swing. In real life, you reversed it. You measured how high the block swung, and working your way backwards, you could then find the incoming velocity of the bullet. Hey, I now know how fast the bullet goes. In this problem, you need to realize that there are two events. Collision and the swing. Jason, what would I use for collision? Manny, what would I use if there's a swingy, curvy path change in height? You know what? Since there's two sections, I'm going to cleverly just go and I'm going to call this here, and I'm going to call this here swing. The bullet hits the block. This is a job for the sum of all the initial momentum equals the sum of all the final momentum. Now look at the picture of the collision. Here's the bullet, here's the block. In the collision, do you see any angles, or is everything in a nice straight line? Woohoo! We'll just let one way be positive, one way be negative, but we're not drawing any triangles. It is true that the block is going to swing up in a yucky, curvy path. Oh, wait a minute. I'm analyzing that one with energy. Scalar. Before the collision, what's moving? The bullet and block both begin with B. How about I'm going to call this mass 1. And I'll call this mass 2. I was going to call them mass A and mass B, but I was worried I get the B mixed up for block and bullet. So I'll go 1 and 2. Before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. So I'm going to have the initial momentum of mass 1. After the collision, what's moving? Mass 1. Why they collide? After the collision. Did I fool you? Did I fool you? What's moving? Mass 1, mass 2, or both? Both stuck together. And Kohei, no angles, straight line, no trig. Woohoo! Kohei, momentum is what times what? P equals what times what? So this is going to be mass 1, V1 initial, right? And again, that equation, although it's on your formula sheet, that's one that's worth having for this unit at least. And it's going to be mass 1 plus mass 2 V final. Am I dulping? Am I drawing vectors? Oh, I like that. Of course, maybe later on I'll give you one where there's also angles. I could, but let's walk before we run. So how would I get V final by itself? Okay. V final is going to be M1 V1 initial divided by M1 plus M2. It's going to be, what is M1? Sorry? Oh, did I give it to you in grams? So yeah, not 0.2, that's 200 grams, 0.02. And we changed it to 200 to get a slightly more interesting question. And then 0.02 plus, was the block 4 kilograms? Okay. After the collision, how fast do the combined masses move off? Sorry, Clay, I don't think I can do this one in my head because 4.02 is a yucky number to do math with. The top is nice. You get 0.995024. I'll go 0.995, but I'll keep this on my calculator. Is that right? Yeah? It's a fluke, almost exactly 1 meter per second. But so 0.995, 0.995. I have a feeling I should have made this go even faster. I was trying to do some quick math in my head, but we'll see. All right. Now they start to swing off. Is there a change in height, Manny? Will there be a change in speed? Well, yeah, because at the top, how fast will you be going for a split second? 0. Is there a yucky curvy path? This is definitely a job for conservation of energy. So I'm going to start out by going KE initial plus PE initial equals KE final plus PE final. And you'll notice I'm not drawing vector symbols. Plus heat, I think we're ignoring friction. The question didn't mention heat. Okay. Oh, here's where we then asked, are any of these 0? Oh, PEI gets hosed again because we're going to decide to let the ground be the height of the block. That's the nice thing about energy. We put the ground wherever we want. Right? Oh, this is actually looking pretty clean because I think I'm going to get this. A half mv initial squared equals mgh final. Is there more than one mass in this question in terms of the picture? Before I start canceling, I better make sure that I can. Which mass is this? The mass of the bullet, the mass of the block, or both? Oh, because we start out with after the collision, when they're stuck together. Are they still stuck together at the top? Hey, we can cancel out the masses. That's always nice when that happens. By the way, what is V initial? The same as what from the previous section? Okay, VF after the collision, at the end of the collision is V initial at the beginning of the swing. We've seen that happen occasionally before in a two-part question as well. What are we trying to find? Oh, how would I get the H by itself? This isn't bad. Is that right? Which is going to be what was it? 0.995. I'm going to use my answer button. Squared divided by 2 times 9.8. What? Great question, Manny. What happened to the 1/2? I just made it a 2 on the bottom. Same thing, and it looks prettier to me. I don't like having a decimal inside of a fraction, but that's just me being me. Squared divided by, well, 2 times 9.8. I actually know that's 19.6. I've done that one so often. Double check me with 2 times 9.8. But you get 0.05 meters, 5 centimeters. 0.051 if I really want to be fussy. You know what? I'll go you know what? 0.0505, because that would be to 3 sig figs, wouldn't it? Because that 5 there, this 0 doesn't count as sig figs. So let's do that. 0.0505 meters, 5 centimeters, which, yeah, I could measure that. Now, Kyle, can you see it would be possible, and this is how they did it back in the old days, if you knew the height, if you knew h, could you find vi, which would be this v right here? So here's my question. If you knew vf, could you find vi of the bullet? Oh yeah, you would divide by the mass of the bullet, and this is why this is called the ballistic pendulum. This is how ballistics was done back in the old days. Now we have, electric eye gate timers and computers that can react faster than that, and good, but okay. So what do I mean by a question that involves momentum and energy? There's a collision and there's a change in height. Really, if you want to really simplify it. Like, here. If each mass is 4 kilograms, and mass 1 starts with 32 meters per second, find the final speed of mass 3 if the hill is 0.82 meters high. Oh, and it says all collisions are hit and stick. What's the fancy word for hit and stick? Inelastic or anelastic? Inelastic? Inelastic. Okay. Let's just walk through this. I don't have to do anything. They collide. Is there a collision? I'll deal with that. Ooh, what happens right here? Change in height? Ooh, they collide. This question's going to have 3 parts. I'm going to try dividing my page into 3. And it's going to be collision 1 into 2. It's going to be, here's the hill. And it's going to be collision 1, 2 into 3, because they stick together. That's not 12 into 3, that's mass 1 and mass 2 into 3. Does that work? I just want to be some way organized, Clay, but I don't want to write a whole paragraph. We can figure out what each section is. All right, let's start. I said collision. The sum of all the momentum before equals the sum of all the momentum after. Before the collision between mass 1 and mass 2, what's moving? Mass 1, this is going to be momentum of mass 1 initial. Knock, knock. Wham, they collide. Stick together, separate, or, both stuck together. So it's going to be momentum both final. Dustin, look at the picture of M1 and M2. Are they in a nice straight line with each other? Woohoo! Oh, excellent. No trig. So now I can go M1 V1 initial equals M1 plus M2. In fact, I think, don't these lines look identical to the lines in the bullet pendulum as well? I think it's exactly the same, essentially. We want, I should remind myself just to be careful with vectors. I'll put the vector symbols on there. We want V final. It's going to be M1 V1 initial divided by m1 plus m2. What did I say each mass was? 4? Yeah, 4 times mass 32. Hey, that's hauling. 32 meters per second, that's around 100 kilometers per hour. Divided by, are you guys okay if I go 4 plus 4 is 8? Do you know why? Because you don't need a calculator for this. Oh, you wimps. What's 4 divided by 8 in lowest terms? This is half of 32. In your head, Dale, without a calculator, what's half of 32? Oh, I weep. Now, is this my final answer? I mean, I could add a direction east, but I'll do my final answer. I'll add a direction at the very, very end because they did say velocity. Okay. Now, they move off. What's the next thing they run into? Did you say a change in height? A change in speed? Kind of a curvy path? You know what? Conservation of energy. Any of these 0? What? Is KEF 0? No, it's actually going to keep some speed at the top of the hill. Otherwise, it couldn't run into mass 3. If it came to a stop, mass 3 wouldn't be worried. Okay. Well, it's going to be a half mv initial squared equals a half mv final squared plus mg H final. Oh, are all of those masses the same? In fact, what is this mass as a number? 8, 8, 8, right? M1 plus M2. So can I cancel the M's out? Yay! What am I trying to find here? What do I want here? I think I want VF. I'm going to do that trick of times by 2, times by 2, times by 2. Cancel, cancel, because that's going to give me VI squared equals VF squared plus 2GH final. How would I get the VF by itself? If I was clever, I would have said, I don't know why, but every once in a while, for some reason, in these energy equations, kids divide rather than subtract. I have no idea why. Okay, so thank you for making me right. Yeah, again, I haven't figured that one out. It just happens. Yeah, definitely minus and then square root. Yes? In fact, I think I'm going to get this. VF equals the square root of VI squared minus 2GH final. Is that okay, Vikas? All right, let's plug and chug. Square root of 16 squared minus 2, 9.8. How high was the hill? 0.82? Okay. Don't know why I picked that. Just making up numbers, I guess. 16 squared minus 2 times 9.8 times 0.82. Square root of that. By the way, at the top of the hill, will it be going faster, slower, or the same? Slower. So if I get an answer bigger than 16, what do I know? I've messed up. Especially if I was like, dividing or something. 15 point, I'll go 489 because this is not my final answer. Is that right? Yeah. So it didn't slow down much at all. Not a very big hill, and I'm ignoring friction, so okay. 15.489. 15.489. That takes us right to here. We keep going, and then what? Oh, we collide. Did I say collide, Dustin? What's that a job for? Conservation of momentum. The sum of all the momentum before equals the sum of all the momentum after. Before the collision, what's moving? Okay, I can write that as mass 1, 2 initial. Does that work okay? As momentum of 1, 2 initial? Right? Bam! They collide. Then what? Sure, that'll work, because I guess the word both doesn't quite work, because both means two, and there's three things. Okay. Manny, looking at the collision picture, are there angles, or are these in a nice... Oh, there's a nice straight line? Oh, I like this. So if I hear you correctly, I think I can go like this. Mass 1 and 2, V1 and 2 initial equals M1 plus M2 plus M3 V final. And we can get the VF by itself, right? VF is going to be M1 plus M2 V initial all over. You know what? I like Manny's suggestion. I'm just going to write M all. That's less writing than M1 plus M2 plus M3. Let's plug in numbers. And I think this is what the question wanted us to find. Oh, 8, right? Mass 1 plus mass 2. 15.489, although I'll use my answer button, divided by, what's the mass of all three of them stuck together? 12? That's kind of nice. 8 times answer button divided by 12. 10.3. Yay! Problems that involve momentum and energy. Now, this was a question that involved momentum and conservation of energy. The other questions I can say is, after a collision, how much energy kinetic did we lose? And I think that's what I did in my next one. Let me see. Oh. I like example 3. I like example 3. I like example 3. Why do I like example 3? Well, first of all, that's some exquisite art. Look at that drawing. I mean, wow, Mr. Dewick. That drawing is so clear, I can totally see what's going on. Well, thank you. I drew it myself.
I see better.
Why else do I like it? Roller coasters. Why else do I like it? Because I like this question, I like this question, I like this question. Okay? Yeah, but you're young. So, a roller coaster with an initial velocity of that rolls down a track, strikes a second roller coaster. They stick together and they go up the next hill. How high can the roller coasters reach? How many parts are there to this question? Yeah, it's 3. First part, change in height, change in speed, yucky curvy path. Wham, they collide. Change in height, change in speed, yucky curvy path. Is that okay? Okay. Well, you know what? That worked so well last time. Let's, draw 3 lines down the middle of our page. And I'll even go so high-tech as to go 1, 2, and section 3. I don't know. I don't care if you label them or how you label them, but it is worth labeling them just to be a bit organized, systematic. Oh, and for all these questions, I would also say I have no problem giving you this answer and asking you to work your way backwards. In other words, I would have no problem giving you this picture and saying, look, if we're going 10.3 meters per second afterwards, how fast was this guy going at the beginning? It would be use this to find VI. Drop that VI down. Now it's VF. You could use this VF to find VI. Drop that down because now it's VF. You could use this VF to find VI. Is that okay? Just for giggles to be different. All right. Conservation of energy. Are any of these 0? Any of these 0? Oh, PEI. Oh, so PEI gets to stick around for a change? Huh. That'll do wonders for their ego. Come on. Really? A province? Come on. I don't know how they pulled that one off. I wonder if any kids from PEI listen to my YouTube videos. That could be interesting. Angry comments. Is the mass the same in all of them? Yeah, because this is before the collision. So I think I can go, yay. What am I trying to find? At the bottom of the hill before the collision? You know what? I'm going to do the trick of times by 2, times by 2, times by 2, so that those 2.5 and those 2.5s cancel. That's going to give me VI squared plus 2G H initial equals VF squared. Hey, how'd I get rid of a squared? Woohoo! So the speed at the bottom of the hill is going to be 8 points, okay? Square root of 8.6 squared plus 2, 9.8. And how high did I make the hill? 18 meters? That's not a bad little roller coastery hill. Could have made it more and funner. And I get 20.658. I'll carry some extra sig figs, or I'll use my answer button. Is that right? Yes? 20.658? Now what? Situation 2. Right? Good. Wham! They collide. Right? Conservation of momentum. So it's going to be the sum of all the momentum before equals the sum of all the momentum after. Before the collision, what's moving? I think mass 1. After the collision, what's moving? Stuck together. It's going to be mass 1 V1 initial equals mass 1 plus mass 2 V final. And I think we already noticed in the collision angles. Oh, straight line, you say? I like that. So how would I get the V final by itself? Divide, someone mumbles. By the bracket, someone mumbles. And I would say, sure. It's going to be M1 V1 initial divided by m1 plus m2. It's going to be, what was mass 1? 250? 20.658 divided by 500, mass 1 plus mass 2. By the way, what is 250 divided by 500 in lowest terms? Really, if two identical masses collide, the resulting speed is half what it used to be. Which, okay, that makes sense to me now that I've thought about it. It's really that divided by 2. 10.329. Yeah? If you use the answer button. Let's go to the top of the hill. And at this time it asks, what's the maximum height? Why is that so nice? Because at my maximum height, what cancels? Speed. Okay. Unlike here, where I said, oh no, we're still moving afterwards. Okay. So, did I say height? It is a change in height. Change in speed, yucky curvy path. But I think in this case, we can at least say that. Oh, and once again, PEI takes its rightful place as a nothing. Right. Can be ignored safely because we're starting out on the ground. Boy, you could take these comments out of context. A half mv initial squared equals mgh final. Let's think carefully. Are both those masses identical? Oh, so I can cancel the masses? Yay! If you aren't sure, you could just put the masses in and you'd find you'll get the same answer. You'll just do more typing than us. You okay with that, Dustin? What are you trying to get by itself? The height. How would I get the height by itself? I would divide by g. Manny, you're okay if instead of writing a 0.5 or a 1/2, I just tuck a 2 in the bottom there because that looks prettier? Even if you're not okay, I'm doing it anyways. I'm going to go just my answer button squared divided by 2 times 9.8 or divided by 19.6. How high will it go? 5.44? So there you go. Lovely concepts from the last 2 units in one question. So I like those questions. I like those questions. Kiowa, I think I said to you, one of the nicest applications of momentum is collisions, and there's some great collisions in football. In football. A 100-kilogram fullback, so fullback weighs about 240, if you want pounds, is running with the football at 2 meters per second. He's met head-on, I don't want to deal with angles, and sticks to a tackler. Which tackler is more likely to stop the fullback? A 200-kilogram lineman moving at 1 meter per second? A 50-kilogram cornerback moving at 4 meters per second? Or both the same? And convince me. What do you think? Yeah? What, first of all, what's the momentum of the runner? Of the fullback? Okay, so let's make a little note here. P fullback equals 200. Yes? I can do that in my head. What do we want his final momentum to be? As a number? 0? Okay, so we want the change in momentum to be, what's change in anything? 0. Question? Yeah. Oh, kilometers per second? Kilogram. You know what? I forgot the G is what? Kilogram meters per second. Thank you. That's what it should be. Yes? I want it to be 0 minus 200. I want the change in momentum to be negative 200 kilogram meters per second. What's the negative saying? That if we hit him, we better be hitting him in exactly the opposite direction that he's traveling. Oh, there's a word for that, head on. So I got that. So now, give me your argument, Manny. And is it enough? Kiowa, my football player, you okay with that? Here's the more interesting question for you as a football player. Which tackle will hurt more? Being hit by a 200 kilogram lineman moving at 1 meter per second, or a 50 kilogram cornerback moving at 4 meters per second? Why? That's the question. Why? Using principles of physics. When we're talking about a collision, what determines the hurt? There's an easier way to think about it, actually. We're just using these numbers. Energy. Because at the end of this collision, how much kinetic energy will there be? 0. Where will it go into deforming the fullback? So, how much kinetic energy does this lineman have? A half times 200 times 1 squared. I think I can do that in my head. 1 squared is 1 times 200 is 200. Dale, in your head, what's half of 200? No calculator required. So this lineman is going to pass on 100 joules of kinetic energy. He's got to go somewhere. Yes, some will go into sound, but let's assume it all goes into the runner. What about this cornerback? Well, he's got a half times 50 times 4 squared. I can do that without a calculator as well. Dale, are you ready? What's 4 squared? What's half of 16? What's 8 times 500? Oh, 50, not 5. Sorry, whoops. Let's fix that. What's 8 times 50? In fact, Kiowa, you could probably safely say it's going to hurt about 4 times as much. Roughly. I mean, there's some leeway in terms of sound and heat and stuff. So using principles of physics, that's why. What are the worst collisions, Kiowa? Where you have the biggest balance between a heavier player who can still move really fast. In football, if you watch NFL or CFL, which position typically has heavier guys that can still move really fast? On defense. Even more than the biggest hits, the ones that make the highlights, it's often the safeties. Because often they only weigh slightly less than the linebackers, but often they have just shy of cornerback speed. Those are the ones, if you go back in the last 20 years, and they'll talk about people like Steve Atwater, people, Ronnie Lott, these were the ones that played safety that could really, holy smokes, deliver a lot of kinetic energy. Is that okay? This used to be this was from a scholarship exam. So we had a bullet traveling parallel to an inclined ramp. You would have drawn the ramp. The ramp has 28 degrees. It drives the block 26 centimeters up the ramp. The coefficient of friction is that. What is the speed of the bullet? You could find all of this. And yes, there's also a collision. And so you could find the speed of the block and bullet. That I would have no problem giving you as a forces question. And then since there was a collision, you could find the incoming speed. I'm going to pass. So I want to give you lots of time to practice this as well. Questions that you could do. If you look at number 1, what's B asking me to find? Wait a minute, work. I don't see a force or a distance, Mr. Dewick. I think you can safely use work equals the change in kinetic plus the change in potential. Wait a minute. Do you see in that picture a change in height at all? And I think you lost kinetic energy, which is why when it says how much work was done, the answer is negative because some energy vanished. Sorry, got to be careful. Some kinetic energy vanished. Probably got turned into heat and sound. Because energy doesn't vanish, it's conserved. Okay, so you can handle that. Number 2 is the ballistic pendulum, except this time it passes through the ballast and exits at 90 meters. So when you do the collision, it's not going to be both stuck together. It's going to be both separate, but you can still find how fast the block would move up and then change in height, change in speed. 3 is good. Look up. That's the key word. You better let one way be positive, one way be negative. 4 is cool, but I'll pass. 5 is good because you guys drive. 6 is good. 9 is good. Hey, why do we follow through whenever we make a stroke in golf or tennis or baseball or hockey? Or why do we tell people, unless you're trying to do a drop shot or something fancy or bunt, but why do we tell people to follow through? Follow through means extend through your swing. In other words, you don't go like this. Look, you've done your weightlifting, you've maxed your force out. The only other variable that you can change is the time of contact because you want to deliver impulse to the ball or the puck or whatever you're hitting. Even if I can go from having an impact of, 2 milliseconds to 4 milliseconds, I've just doubled the velocity because the mass didn't change. So, you know what? We just talked about it. You can skip that one now. I'll let you think about number 12. That's a nice baseball-y, sportsy question. Is it easier to hit a home run off of a fast pitch or off of a slow pitch? Okay, I'll let you think about that. Using principles of physics, explain your answer.